Hello all, this is Mr. G and this is our warm-up for today's lesson. So pause the video right here, give this problem a shot, come back when you think you have an answer. We're going to 3, 2, 1, let's go. It says a group of farmers wants to make as much money selling their crops as they can. They can grow corn or wheat. How much of each crop should they grow? That's the question. And basically, we don't have nearly enough information to answer this question. So the answer is, I don't know. We need way more information than this. And I want to be really specific about the type of information we need. Because we could say like, oh, we need to know like how much they can sell each crop for. We need to know like what type of weather is good for each crop. But even like put all that aside, we need to know what this group of farmers' limitations are. We need to know what their constraints are. So, like how much farmland do they have to grow their crops on? How much time do they have? How much are they paying their workers to get all this stuff done? Does it change versus like with one crop or the other? We need to know what the limitations are. Like we could give this problem to maybe like a 5-year-old or something, and they might say, "Oh, they should grow like 1,000,000 pounds of each." It's like, well, okay, that might not be feasible. All right, so that really leads us into our objective. So we're doing chapter 3, section 4. Our objective today. After here, we should be able to use linear programming to find maximum values based on constraints. Use linear programming to find maximum values based on constraints. And there's that key word for today, constraints. Because we are constrained by things. Just that's part of being alive. That's part of the human condition, you could say. Like it's very easy to think like, oh, I can do anything. I've certainly had moments of egomania, you could say, where I'm like, oh yeah, I can definitely do anything. I can definitely do that. Then I tried to do that thing I thought I could do. It's like, wow, this is a lot harder than I thought it could be. And the older I get, the more that seems to happen, unfortunately. So we all have limitations. We all have constraints that we need to take into account. And linear programming is essentially just a process, a strategy that helps us assess a situation, look at the constraints, and come up with a maximum or minimum value as well. But most of the time, we're worried about maximizing something. I guess not always, but that's what we're going to be dealing with in this lesson, maximizing values. So what we have here, this is an example of how linear programming works. A very simple example, and um, many of you just while I'm talking, if you're reading this, you might immediately get to the answer. Oh, I know how. What's the most money we can make? Why is Mr. G going through all these steps when I just got the answer in my head? We're starting with a very basic, easy to understand problem, so we can understand sort of our strategy. So that when we look at a more complicated problem, we've got the strategy already in our mind. That's the goal for this example. So it says we're doing a candy bar fundraiser, and what's the most money we can make? We want to make as much money as possible in this candy bar fundraiser. So let's take a look at this chart right here. We're selling two different types of bars. We got a regular chocolate bar and then a chocolate with caramel. Sounds tasty. So profit per bar, we can make $5 profit per chocolate bar and $7 profit for chocolate with caramel. And then number you can sell. We can sell 18 of the chocolate bars and 12 of the chocolate with caramel. So these are our constraints right here. We are constrained. We are limited in the amount we can sell. We can't sell 1,000,000 of each or 1,000,000,000 or something like that. It's like, okay, we've got 18 to sell of the chocolate and 12 to sell of the chocolate bars with caramel. Right? We are constrained. Now, whenever you do linear programming, you want to write the objective function. Now, the objective function is whatever we're trying to maximize or minimize, but in this class, we're going to focus on maximizing things. So the objective function is whatever we're looking to maximize, and here we're looking to maximize profit. That's what the P stands for. So it says profit equals 5x plus 7y, and hopefully you see where this comes from. It comes from the amount of profit we can make per each type of bar. So essentially what they said is, okay, we're going to make X's the chocolate bars and Y the chocolate bars with caramel. So 5 times X plus 7 times Y will give us the total amount of profit because it's 5 per X and 7 per Y. That gives us the profit. Now, we don't know what the profit is. Remember, that's why we don't have a number here. We're not going to solve this. There's lots of different possible values for X and Y. We're looking for the values in X and Y that will give us the most profit, the biggest amount of money made. So after the objective function, when we're doing linear programming, again, we're practicing this strategy, we have to worry about our constraints. We have to worry about the limitations set on us. So they're already written here. It says x is less than or equal to 18. Let's focus on that first one. Well, x is less than or equal to 18. Well, x was the amount of chocolate bars, and it's saying the number of chocolate bars we sell is less than or equal to 18, and that makes sense because 18 is the maximum number we can sell. Okay, so X has got to be smaller or equal to 18. Then we've got Y is less than or equal to 12. And again, that pretty much makes sense. It's saying Y, the chocolate bars with caramel, the most we can sell is 12. And look at that. The most we can sell right there is 12. Now, these two constraints, sometimes students have a harder time seeing where they come from. It's like, okay, I see the 18, I see the 12. Where are these zeros coming from? It's saying X is greater than or equal to 0, and Y must be greater than or equal to 0. Essentially, what we're saying there is the number of chocolate bars we sell and the number of chocolate bars with caramel that we sell must be a positive number or 0. So it basically must be non-negative. That's a better way to say it. They must be non-negative. And that really makes sense because, you know, I would never say, oh, I sold -5 chocolate bars in this fundraiser. That would make no sense at all. The things we sell have to have positive values. I guess maybe there's some weird exception with like stocks or something like that. Things go negative. I don't know. The stock market's crazy. We're not worried about that. We're worried about a nice simple chocolate bar fundraiser, and we don't sell negative amounts of chocolate bars, only positive. Now, those two constraints, I guess I need to circle them one more time or box them just to show you where I'm looking. Those two constraints, we don't always list them. Whenever we're doing a linear programming problem, unless there's some weird situation where things can go negative, we just assume, okay, we're only dealing with positive numbers. We're only dealing with positive values, or I should say non-negative values. That's a better way to say it. All right, and then once we have our constraints, we want to look at what's called the feasible region. The feasible region is what we have here. Now, this is essentially our constraints graph. Hopefully this looks pretty familiar because we just did a lot of work graphing systems of linear inequalities, and that's exactly what the constraints are. They're a system of linear inequalities. And the feasible region ends up looking like this. So this is the line, what was it? Y equals 12, so we're shading below that line. This is the line X equals 18, and we shade to the left of it because X must be smaller than that. So we end up with that shaded region. So all of the ordered pairs in here are possible solutions. They're possible correct values. So like even this point that's not drawn in, 17, 1, 2. So this point right here, which is 17, 3, if I counted that correctly, 17.3, that means, okay, this is the situation. That point is the situation where we sold 7 of the X bars and 3 of the Y bars. So that would be, what were they? 17 chocolate bars and 3 chocolate bars with caramels. All right? So you might be thinking to yourself, wait a minute, so all these shaded points are feasible? All these shaded points are possible? So does that mean to find the maximum, we have to check every single one of these points? No, we don't. Fortunately, a key with linear programming, and you've got to write this down. One of the keys with linear programming is we get the maximum and minimum values from the vertices of the feasible region. We get maximum and minimum values from the vertices of the feasible region. So what that means in practice is if we look at a feasible region, we don't have to check every single shaded point. We only need to check the vertices. We only need to check the corners. So we take these corners, we take each of these situations, and we plug them back into our objective function, our equation for profit, and see which gives us the biggest profit. Now, hopefully you can sort of automatically see, well, wait a minute. If we sell, 18 of one and 12 of the other, if we sell everything we can, then that's going to give us the most profit. I'm not going to waste our time plugging all these numbers in. Hopefully you see that's going to give us the biggest profit, the most amount of money made. So that's the strategy for linear programming. Okay, so look at the objective function, figure out an equation for what we're trying to maximize, then look at the constraints, look at the constraints, okay, what's limiting us, and then finally look at the feasible region, graph our constraints, and check the vertices against our objective function. Okay. Now, that was a whole lot of talking. Let's actually do one of these problems. Now, this one's going to be kind of simple. Let's take a look here, or hopefully we're sort of baby stepping here, taking our first steps into this process of linear programming. All right, let's take a look here. So now we've got a bake sale going on. This is example 2. They give us some information in a chart, which is good, so let's take a look at that. We've got 2 types of bread we're making, it looks like. Pumpkin bread will make X, and Irish soda bread will make Y. So we've got the cups of flour that are required for both. So a loaf of pumpkin bread requires 3 cups of flour. Irish soda bread, we need 5 cups of flour, and we've got different amounts of profit we can make per loaf. So we're making $4 profit for pumpkin bread and $7 profit for Irish soda bread. Now keep in mind, that does not mean we're charging $4 and $7 for the two respective types of bread. That's the profit we're making. So, like if our costs for the pumpkin bread are $2, then that means we have to charge $6 to get our $4 profit. So remember, profit is sort of cost minus, or not cost, what you're charging minus your cost. That's what profit comes out to. Got off on a little tangent there. Let's keep reading. It says you can't make more than 3 loaves of Irish soda bread. Okay, so that's a constraint. Can't make more than 3 loaves of Irish soda bread, and you have a total of 30 cups of flour. That's going to be another limitation. Because remember, we can't just make a billion of each of these. There's limitations. We've only got so much flour to work with, and we can only make 3 loaves of Irish soda bread. Maybe we only have 3 pans for that particular type of bread or something. All right, so let's start our linear programming process. First thing, we write our objective function, the objective function. So that's what we're trying to maximize. It's saying, what's the maximum profit? Okay, so P equals, let's see. The profit we can make for a pumpkin bread is 4, so that would be 4x, plus the profit we make for Irish soda bread is $7, so that'd be 7y. So that's our objective function. Our profit is going to be 4x plus 7y. $4 for every loaf of pumpkin bread plus $7 for every loaf of Irish soda bread. Now we need our constraints. We need our limitations because there's limits on what we can do. Let's scroll down a little bit. So let me see. Now I've got to scroll right back up, ironically. The first one I want to talk about is this one right here. Because that one's going to be the easiest. It says we can't sell, or we can't make, rather, more than 3 loaves of Irish soda bread. So that means the y value, the Irish soda breads have a ceiling. Y must be less than or equal to 3. Less than or equal to 3. Now let's take a look at the other one. The other limitation they have, or they give us rather, has to do with the total amount of cups of flour we have. So that's going to be involved with the 3 and the 5. So basically, the amount of cups of flour we use has to be less than or equal to 30. So it's going to be something is less than or equal to 30 because that's our maximum. That's our ceiling. Now let me take a look here. We can use 3 cups of flour per pumpkin bread, so that would be 3 times x, 3 cups of flour per pumpkin bread, plus 5 cups of flour per Irish soda bread, so that would be 5y. Let me double check those numbers one more time. 3x plus 5y, yeah, I'm looking right there, just to focus you on where my eyes are going. All right, so these are our constraints. Those are our constraints. Next up, what we have to do is graph our constraints, take our system of linear inequalities and actually graph them so we can see what we're looking at. Now this first one, we do this in green, this one's ready to go. We can just throw that one right in a graphing calculator. We might not even need a graphing calculator to graph that. But this second one, we do just a highlight in red, that's going to take a little bit of work because in a graphing calculator, or even if we want to graph on our own, it's always easier if y is by itself. And in fact, if we're going to use a graphing calculator, at least a TI-84, we need y to be by itself. So let's get y by itself. We should be good at that by now. I'm going to take away 3x. Get 5y is less than or equal to, that's supposed to be an x, negative 3x plus 30. Divide everything by 5, so we distribute the division on the right side to both terms. A little bit more space so my face is out of the way. We get y is less than or equal to negative 3/5 x plus 6. All right, now it's time to plug these into our graphing calculator so we can see our feasible region. Let's hit y equals. Y1 will be 3. There actually is a way to change this equal sign to a less than or greater than. I think it's more trouble than it's worth, to be honest with you. I'm just going to leave it as an equal. So if you want to try and mess around with that, by all means, go for it. And the next one is, let me scroll this down so I can see, negative 3 divided by 5x plus 6. And then we hit graph. And there is our feasible region. Or rather, that's the graph. But let's make sure, let me jump to the next slide for this. Here's what it looks like. Where's the feasible region? So let's think about this. Suppose y is less than, so that means we shade below. So we would shade below the diagonal line and below the horizontal line. Which means that the shading is overlapping in this whole area right here. Overlapping all there. And just to make it real obvious, I'm just going to put some lines going this way as well. That's where the shading is overlapping. But our feasible region is not all of that. There's some parts of this quote unquote feasible region that aren't feasible. So we don't actually have our feasible region yet because we can't have any negatives. All right? We're selling actual loaves of bread here. We're not going to sell negative loaves of bread at the bake sale. So that means we don't care about anything going on in quadrants 2, 3, or 4 because they include negative values. We're only interested in quadrant 1. So our feasible region ends up looking just like that. It's just this trapezoid, if you remember your geometry. It's just that trapezoid. So now I'm going to jump back and draw what that feasible region looks like. A little bit more space. Go down. Come on. So here's what the feasible region looks like. Again, I know my drawing's not perfect, but that's the trapezoid we're looking at. Actually, that's horrendous. I'm doing that again. That's a little better. I'm not going to do it 3 times in a row. We'll just fix it real quick. Okay, cool. Whatever. All right, so now what we need to do is, okay, what points in this feasible region do we need to check? We don't need to check all of them. We just need to check the vertices. Remember, that was the big key with linear programming. To find the maximum or minimum value, it's going to happen at one of the vertices. Well, this point, obviously, that's the origin. So we can pretty much cross that out because this point, that's where we sell neither of each. So that's definitely not going to give us the most amount of money. And we can actually use the TI-84 to give us the ordered pairs for the rest of these points. We just have to know what to look for. So this point right here, that point is going to be a y-intercept. That's a y-intercept because it's right on the y-axis. To find a y-intercept, we just do second table, and there we go. But if you look, it's actually giving us 2 possibilities. It says where x equals 0, y1 equals 3, and y2 equals 6. So this is either going to be 0, 3 or 0, 6. And we can tell by remembering what our function actually looked like, or rather what the graph actually looked like. There were 2 y-intercepts. Okay? So do we want the one that's at 6 or at 3? Hopefully you're saying, oh, we want the smaller one. That's going to be at 3. So I can jump back, scroll back down, if it'll let me. There we go. And it's 0, 3. Right, now, we're just moving right along, think, okay, what's this point going to be? Well, that point's going to be where they cross, so that's an intersection. Well, we know how to find an intersection. We just hit second, calculate, 5 for intersect. I'm going to move over to get closer to this intersection. I think that should be close enough. I'm going to hit enter, enter, and enter. And there we go. The intersection is 5, 3. Last but not least, we have to find this point down here, which is a real root. That's an x-intercept. So we know how to do that. We get second, calculate, 0, because 0, real root, x-intercept is all the same thing. Now, if you look at this graph, see how it looks like the real root is like barely on the screen? Before I hit left bound or right bound, I'm going to move my cursor to the right. Oh, I'm on the wrong function. Let me hit down to get to the right one. I'm going to move my cursor to the right and move the screen a little bit. Yeah, now we can see the real root a little bit better. We can see rather around the real root better. So now let's go back to the left of it and hit enter for left bound and move to the right of it. Hit enter for right bound. We don't care about guessing, so we just hit enter again, and we've got 10, 0. 10, 0. So these are the 3 situations we have to check. This situation is, okay, that's where we make none of the, which one was X? The pumpkin bread, I think? Yeah, we make no pumpkin breads and 3 Irish soda breads. This one is, okay, 5 pumpkin breads and 3 Irish soda breads, so we sort of hedge our bets and do a little of both. And this one down here is we go all in with the pumpkin bread. Forget the Irish soda bread, we make 10 pumpkin breads and no Irish soda breads. To figure out which one of these is best, we need to look back at our objective function, which was 4x plus 7y, 4x plus 7y. 4x plus 7y. Now what we're going to do, we're going to take these ordered pairs and plug them in. See which one gives us the biggest profit. Let's do 0, 3 first. I think we can do a lot of this in our head. 0, 3, that would be 4 times 0 is 0, plus 3 times 7 is 21, so that would just be 21 for this first one. So that would be $21 of profit. For 5, 3, that would be 4 times 5, that's 20. plus 3 times 7 is 21. That would be $41 profit. And then last but not least, 10 zeros. So that'd be 10 times x is 40, plus and 7 times 0 is just 0. And we end up with $40, which means the most amount of money we can make is $41. That's our answer when we make 5 pumpkin breads and 3 Irish soda breads. So this was our first real linear programming problem. And hopefully you're seeing that this has some really obvious applications to the real world. I mean, small businesses, they're constantly trying to maximize and minimize things. You want to maximize the money coming in, minimize the money going out, trying to stay in business, providing for families and stuff like that. Let's take a look at number 3. I want you to try this example on your own. Now, the graph might be a little bit weird for this one, but you should know how to zoom in or out so you can see a good enough picture. But I just want to give you that little heads up before you try this one on your own. But pause the video right here, give this problem your best shot, and come back when you think you have an answer. We're going over to 3, 2, 1, let's go. All right. So here we're making headbands and wristbands. We've got different times to make them, different amount of fabrics needed for them, and different amount of profits we get for them. And we've got some constraints right here to deal with. We have 180 minutes to spend working, and 1,400 square inches of fabric that we can use. So those are two pretty big limitations. What's our maximum profit? Let's start with that. Let's start with an equation for profit, our objective function. There we go. Let's make headbands X and wristbands Y. So then our profit would be 6 per headband, that'd be 6x, plus 4 per wristband, that's 4y. So there's our objective function. That's what we're going to use at the very end to figure out which combination of the headband and wristband gives us the biggest profit. All right, now we need our constraints. So the first limitation is the amount of time we have to work. So the amount of time we spend working is going to be less than or equal to 180 minutes. If it takes 10 minutes per headband plus 6 minutes per wristband, that's got to be less than or equal to 180. So there's our first constraint. Now I'll tell you what, we know we're going to have to get y by itself eventually, so let's just get y by itself right now. Let's just get it by itself. So let's take away 10x from both sides. That 6y is less than or equal to negative 10x plus 180. Then we're going to divide by 6, distribute that division to everything we see, and that comes out to y is less than or equal to, simplify that fraction, divide them both by 2, we get 5 over 3x plus 30. My face is in the way there, but we can slow the page down. Let's put that right in the calculator now, just to sort of save some time. Negative 5 over 3x plus 30. We're not going to hit graph yet, though, because we've got one other constraint to worry about. Let's do this in green just to keep them separate. The 1,400. We don't have an unlimited amount of fabric. We are restricted. We are constrained. We are limited just because, that's how the world works, unfortunately. It'd be great if we had unlimited of everything, but, resources are limited. What can you do? So 1,400 square inches. Let me see. So we're focused on this column right there, the amount of fabric needed. So that would be 100 per headband, so that's going to translate into 100x plus how much per wristband? 40 per wristband, so that's 40y. Has to be less than or equal to, what was it, 1,400? Yeah, 1,400. All right, now I'm going to scroll down so we can get y by itself. We're going to take away 100x from both sides. That gives us 40y is less than or equal to negative 100x. I did not write x's today. It's still hideous. Try this one more time. There we go, that's better. Oh, I got distracted. Negative 100x plus 1,400. And now we divide by 40. Distribute the division over there. And let's see what we get. Y is less than or equal to, we can cancel out those zeros. So that's going to be, let's see, divided both by 2. That's negative 5 over 2x. 5. And then the 1,400 divided by 40 becomes plus 4. So we cross off those zeros. 4 goes into 14 3 times. With 2 left over, 4 goes into 25 times. So we get 35. Now let's plug that right into our graphing calculator. So that's negative 5 over 2x plus 35. And now we're ready to graph. And yeah, like I said, we don't see the full picture here. We get some of it, but not all of it. So we could hit zoom 6 to get back to a standard window, but we don't want to do that. We want to zoom out. So we're going to hit zoom, go to zoom out. We can move our cursor to where we want it to zoom out from. I think if we make that the center, that would be okay. It doesn't have to be exactly there, just anywhere should be fine. There's one line, that's a much better picture. All right, so let's sort of draw a picture, an approximation of what our feasible region looks like. Because remember, it's just the trapezoid. Everything in quadrant one that's below both of the lines. So it's going to look something like this. I know my drawing's not perfect, but it looks something like that. It's that trapezoid. All right, so now we've got to find our 3 points. Because we know the origin, 0, 0, that's not going to give us the maximum value. We've got to find our 3 vertices. Let's start with the y-intercept, which is going to be the one right here. So let's see. So I'm going to go to second graph. Remember, since we shaded below both of them, we want the smaller of the y-intercepts. At x equals 0, we've got a y-intercept of 30 and 35. That means we want 30, so 0, 30. We always want the smaller one, at least when we're shading below both of them. If we're shading above, then things change. But we're shading below, so we want the smaller one. Now we've got to find this point, which we remember hopefully is an intersection. Second, calculate intersect. Move over to the right. Actually, we're pretty close already. I'm going to hit enter, enter, enter. And that gives us, what's the intersection? 620. So 620. So that's 6 headbands and 20 wristbands. And then finally, we need our real root. We need the 0 down there. Second, calculate 0. Now we're going to move over to our x-axis. Let's make sure we're on the right function. We are not. I'm going to hit down to get to the other one. Oh, now I'm past it. Hit left. That's to the left of the real root. Hit enter. Past the x-axis. Hit right for right bound. Enter, because we don't care about guessing. And we get a 0, 14, 0. 14, 0. All right, now last step. I know this process is long, but once you practice it a few times, you get a lot faster at it. Now we're going to take those 3 values and plug them into our objective function, which was 6x, 4y. So 6x plus 4y, that's what profit equals. All right, I think we can do a lot of this in our head. Let's see. So 0, 30, that's going to be obviously 6 times 0, that's 0, plus 4 times y, that'd be 4 times 30, that's 120. So that would come out to $120. So we can make $120 of profit with that one. With 620, I'm going to need a little bit more space. 620, that'd be 6 times 6, that's 36. Plus 20 times 4, that's 80. And that comes out to 116, if I'm doing that correctly. 8 and 3 is 11, and 6, yep, 116. So $116. And then last but not least, 14, 0. So that'd be 6 times 14. That's 60 and 24. That's 84 plus 0. And we get $84. So which one gave us the most amount of profit? It's this one right here. $120 is our maximum profit using 0, 30. So basically, to make the most amount of profit here, Y was the wristbands. Yeah, so we don't want to make any headbands. We want to go all in, make as many wristbands as we can, given our constraints. All right, I know that was a lot. This was probably a longer video than usual, but hopefully it makes sense. If you have any questions, by all means, let me know. Enjoy the rest of your day.